Page 5 of discrete random variables, number 6, I think it is. In a mathematics competition, students try to find a correct answer from 5 options in a multiple choice exam of 25 questions. Alex decides his best strategy is to guess all the answers. Does this sound familiar? This is kind of what we studied in the investigation. The difference is this is 25 questions instead of 40 and 5 multiple choice options instead of 4, but otherwise it's similar. State an appropriate models for the random variable A equals the number of questions Alex gets correct. So this is a binomial distribution, and the n value is 25, and the p value is 1 over 5, right? Because randomly guessing, you have a 1 over 5 chance of guessing the answer correct. So the random variable A is this distribution. Find the probability that the number of questions that Alex gets correct is at most 5, at least 7, no more than 3. So these are all questions where all you need to do is frame it in the right format so that you can use bin PDF or bin CDF to answer them. Okay, and so the first one is at most 5, and if we wrote that as a math expression, it would be less than or equal to 5, at most 5, so that includes 5, right? At most 5. So yes, x is less than or equal to 5 is B. So we would use CDF for this one, and the x value would be 5. And of course the n value is 25, and the p value is 1/5, right? So let's do that. We're going to do binomial CDF. Biggest challenge is to actually turn on the calculator. Okay, and so we go to second distribution, second page, we do binomial CDF, because CDF does less than or equal to. And then we're going to put an n value of 25 and a p value of 1/5, which is 0.2. You could put 1/5 also. And the x value is 5. And the answer is 0.617. Okay, so that was the answer for B. And then what about C? At least 7. At least 7, is it greater than or equal to? Is it greater than or equal to 7? At least 7, does it include 7? Yes, it does. At least 7 is x is greater than or equal to 7. So now we cannot do x is greater than or equal to 7 on the calculator because the calculator is only capable of doing a less than or equal to problem. But we can set this up as 1 minus the probability that x is less than or equal to 6, right? Because if we want x is less than or equal to greater than or equal to 7, we want 7, 8, 9, dot, dot, dot. How do we subtract off the numbers that we don't want? We do for x is less than or equal to 6 because that subtracts off 0 all the way to 6. Okay, so what is this binomial CDF for 6? So we could just like copy this and replace 5 with 6, and that'll give us the answer for 6. So the answer for 6 is 0.780, so it'd be 1 minus 0.780, which is equal to 0.220. Okay, so that was the answer for at least 7. What about no more than 3? No more than 3. That is no number that is more than 3, so that would be less than or equal to 3. Is that right? Probably that x is less than or equal to 3. No more than 3. Yeah, that's right. So in this case, we would want x equals 3, and we can just do a straight up CDF because it's less than or equal to, which the calculator is capable of doing. So now we just need to take the CDF and then replace the 6 with 3, and that would be less than or equal to 3, which is the same thing as no more than 3. And the answer is 0.234. 234. Okay, so that was D. All right, and let's see, next one. Write down the expected value of the random variable a and interpret this value. So remember, if you look at the formula sheet, if you look at the expected value of x formulas, it says that that's equal to n times p. So in this case, expected value of the random variable a, we know what the n and p are. The n is 25. And the p-value is 1/5. So 25 times 1/5 is 5. Oops. 25 times 0.2 is 5. Okay? So the expected value of A is 5. And what does this mean? It means that his expected score is 5. Okay, expected score is 5. Or if he did this multiple times, that would he would get an average score of 5. Find the probability that Alex scores more than the expected. So what is the probability that Alex gets? I kept writing x, but actually the random variable in this case is actually a. Scores more than expected, so greater than 5. So that would be the same thing as, so the calculator doesn't do greater than, right? It only does less than or equal to. So we could set this up as 1 minus the probability that a is less than or equal to what? 5? Yeah, because we want a is greater than 5, so we subtract off all the numbers from 0 to 5. And so that would be, what is the probability that a is less than or equal to 5? So we're going to do the same thing we did before. Binomial CDF with n equals 25 and p equals 0.2, except now we're going to put 5 for the x value. We want binomial CDF because it's less than or equal to 5. Okay, and the answer is 0.617. Oh, it's 1 minus 0.617 because it's 1 minus the probability that a is less than or equal to 5. So 1 minus so the answer is 0.383. Okay. G. In the test, a correct answer is awarded 4 points. An incorrect answer incurs a penalty of 1 point. If Alex guesses all the questions, find the expected value of his total points for the examination. Well, we already know that the expected number of correct answers he's going to get is 5, right? So we could just use that result to figure out this question. So basically, he has 5 correct questions and 20 incorrect questions. The 5 incorrect questions are going to incur a penalty of 1 point. And the 5 correct questions are going to incur an award of 4 points. The 20 incorrect questions are going to incur a penalty of -1 points. And so that is going to give us his total points. 5 times 4 is 20. The penalty of -1 times 20 is going to be a subtract 20. And so his score is going to be 0. Okay, so that's kind of planned by the designers of the test. They make it so that guessing doesn't really get you ahead of what you would get if you didn't do the exam. So guessing basically is going to give you a score of 0. That makes sense, right? Okay, number 7. Calc Air buys a new passenger jet with 538 seats. For the first flight of the new jet, all 538 tickets are sold. Assume that the probability that an individual passenger turns up to the airport in time to take their seat on the jet is 0.91. Write down the distribution of the random variable t equals the number of passengers that arrive on time to take their seats, stating any assumptions you make. Okay, so this is going to be t is a binomial distribution with 538 repetitions and 0.91 as the individual probability of the thing happening or not. Okay, and as far as assumptions, we know the information they gave us, which is that there are 538 separate tickets, and each individual passenger has a 0.91 chance of coming. The only thing you really need to assume is that each individual passenger coming is independent from the other individual passengers coming. So that's kind of a bad assumption in some cases, because think about it. Some of the passengers are together, right? You might have a couple, or you might have a family or something, and if one doesn't come, all of them, the whole group doesn't come. So it's not completely right to use binomial distribution in this case, but it's a good approximation, okay? Find the probability that t equals 538 and interpret your answer. So if t equals 538, that means x equals 538. So we're saying, what is the probability that you have exactly 538 people come when you have 538 chances and each person has a 0.91 chance of coming? And so the x value would be 538. And would you use PDF or CDF? Well, in this case, we're looking for exactly 538, so we would use PDF. So let's go to binomial PDF, and then we'll put 538 for our trials, because there's 538 seats. We'll put 0.91, because that's the probability that one person is going to show up. And then, oops. .91, and then the x value is going to be 538 also. So basically, what's the probability of perfect attendance? I'd say it's going to be pretty small. Okay, it's really small. 9 times 10 to the negative 23rd. So 0.0000, 22 zeros, and then 921. Okay, so there's not really a way to write this easily without doing scientific notation. So let's go ahead and write it in scientific notation. It'll be 9.21 times 10 to the negative 23rd. Interpret your answer. So this is the probability that everyone comes. Everyone on time. So this kind of like shows you why do planes overbook, right? Planes need to fly full in order to make a lot of money, or make the most money possible on a plane. If they only sell exactly the number of tickets that the plane holds, then they're always going to have empty seats, and they don't want to fly with empty seats. So what they do is they book more seats than they have, and then if they go over, it's not going to go over often, and when it does go over, then they'll pay those people to take a later flight, and it's going to be a lot less money than the money they lose flying with a bunch of empty seats. Okay? Find the probability that t is greater than or equal to 510 and interpret your answer. Now remember, the calculator is incapable of calculating a greater than or equal to problem. It only can do a less than or equal to problem. So we need to convert this into a less than or equal to expression. So that'll be 1 minus the probability that t is less than or equal to, would it be 510? It wouldn't be 510, because t is greater than or equal to 510 includes 510. And less than or equal to 510 also includes 510. So we need to reduce it by 1 in order to not have overlap. So we're going to subtract probability that t is less than or equal to 509, and then it'll work out perfectly, right? Now that we have less than or equal to, now we can use the binomial CDF function on the calculator, because the binomial CDF function figures out exactly that. It figures out less than or equal to. So I just put 509 there instead of 538. I'm sorry, I need to do binomial CDF, not binomial PDF. So I cannot just copy and paste that one. Be careful. So I'm going to go up to binomial CDF, and then I'm going to do 538 and 0.91. And the x value is going to be 509. And then we'll see what is the probability that they have at least 509 people on the plane. And the answer is 0.999. And so the probability that you have greater than or equal to 510 is very small, but not as small as 10 to the negative 23rd, right? It's actually 6.7 times 10 to the negative 4th, or 0.000675. But still, I'm sorry, 672. Still, really small probability, right? Really small probability that you even have more than 510 people. So that's pretty depressing. You really need to overbook, especially if this is true. If it's 0.91 chance of each person arriving, definitely need to overbook. Find the expected number of passengers who arrive at the airport on time. Now remember, expected value is calculated by n times p. So we're going to do n, which is the number of total tickets sold, times the probability that the person shows up. Whoops. 538 times 0.91, which is 489 or 490. Okay, so the average number of people that are going to come under these conditions is 490, which is a lot of empty seats, right? That's 48 empty seats. So yeah, but do you see how like maybe binomial distribution is good for business reasons, right? You could this is like a business scenario, and you use probability to figure out a very practical thing, which is how much should they overbook in order to get close to filling up their plane every time. Okay, so that's it for this page 5.